Imagine sending a spacecraft to one of the most massive planets in our solar system, not to land or orbit indefinitely, but to be intentionally destroyed. That's exactly what NASA did with the Galileo spacecraft on September 21, 2003. Galileo was deliberately steered into Jupiter's thick atmosphere, where it was obliterated within seconds, not because it failed, but because its mission was complete and NASA wanted to avoid an unacceptable risk. Galileo was no ordinary probe. It cost nearly $1.4 billion, operated for almost 14 years, and delivered some of the most valuable insights ever gathered about Jupiter. But letting it drift aimlessly risked contaminating one of Jupiter's moons, Europa, which might harbor life beneath its icy crust. So, NASA chose to end Galileo's journey in Jupiter's crushing atmosphere, ensuring no chance of accidental contamination. The data Galileo sent back during its descent was puzzling. Scientists expected to find a stormy, water-rich atmosphere, a place teeming with clouds and turbulence. Instead, the probe plunged into one of the driest and calmest regions imaginable. Temperatures were hotter than predicted, and winds blew faster than anyone anticipated, over 370 miles per hour, and these fierce winds didn't ease even 100 miles beneath the cloud tops. But the greatest surprise was the scarcity of water. Jupiter formed beyond what's called the frost line, the region in the early solar system cold enough for water ice to form. It should be bursting with water vapor. Yet, Galileo found very little. For years, scientists were baffled. How could a giant planet, born in a frozen zone, be so dry? The answer came when researchers realized the probe had descended right into a hot spot on Jupiter, a rare area where clouds thin out, allowing heat from deep inside the planet to escape. These hot spots are essentially deserts in Jupiter's atmosphere, where dry, descending air suppresses cloud formation. So, Galileo's data was like sending a probe to Earth, landing it in the Sahara, and concluding Earth is a desert planet. While Galileo's atmospheric probe was busy collecting data, the main spacecraft continued orbiting Jupiter, revealing even stranger facts. Jupiter's atmosphere isn't a simple layer of gas. It extends thousands of miles deep, blending seamlessly into thick layers of liquid, with no clear boundary. Pressure and temperature skyrocket as you go deeper. At the cloud tops, pressure equals Earth's sea level atmosphere, about 1 bar. But 1,000 miles down, pressure reaches an unimaginable 200,000 bars, 200,000 times Earth's atmospheric pressure. Under such extreme pressure, hydrogen inside Jupiter stops acting like a gas and transforms into a strange liquid metal. This liquid metallic hydrogen is unlike anything naturally found on Earth. Electrons get stripped from hydrogen atoms, turning it into an electrically conductive metal. This exotic state makes up most of Jupiter's interior, between 3/4 and 9/10 of the planet's mass, and it churns violently, driven by heat from the planet's core. This churning metallic hydrogen, combined with Jupiter's rapid spin, generates the planet's colossal magnetic field. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times more powerful than Earth's. At the equator, it measures roughly 4.3 Gauss, and near the poles, it peaks at 14 Gauss. For comparison, Earth's magnetic field is only about half a Gauss at the surface. Jupiter's magnetosphere, the region dominated by its magnetic field, is enormous. It stretches 7 million miles sunward and extends more than 600 million miles in the opposite direction, almost reaching Saturn's orbit. Within this vast magnetic bubble, charged particles accelerate to near light speed, creating intense radiation that can fry spacecraft electronics in mere hours. Galileo was specially fortified against this radiation. It carried heavy shielding and used radiation-hardened electronics designed to survive Jupiter's deadly environment. Even so, the spacecraft suffered. Over 34 orbits, it endured radiation equivalent to 60 million dental X-rays, enough to be fatal to thousands of humans. Its cameras failed, instruments died, and memory errors plagued its onboard computer. NASA's Juno spacecraft faces the same radiation gauntlet. Launched years later, Juno entered Jupiter's orbit on July 4, 2016, equipped to study the planet's interior by measuring tiny changes in its gravity field. Gravity varies with the distribution of mass, so by mapping these fluctuations, Juno revealed startling new details about Jupiter's core. For decades, scientists believed Jupiter had a solid, compact core made of rock and ice, roughly 10 to 20 times Earth's mass. This fit the classic planet formation model, starting with a rocky seed that grew by pulling in gas. But Juno's findings upended this idea. Jupiter's core isn't a neat, dense ball. Instead, it's fuzzy and diffuse, stretching out to nearly half the planet's radius. Heavy elements gradually blend into the surrounding metallic hydrogen, with no sharp boundary in sight. This unexpected, fuzzy core puzzled researchers. Some suggest Jupiter had been struck by a massive protoplanet early on, mixing its core with gaseous layers. Simulations showed such a collision could scatter core material. But other models indicated this mixing should be temporary. Over time, heavy elements would settle back into a compact core. Yet Jupiter's fuzzy core has persisted for billions of years. A newer theory posits that Jupiter's core formed gradually during a chaotic, uneven accretion process. The idea gains support from observations of Saturn, which also seems to have a fuzzy core, suggesting this might be a common trait among gas giants rather than a random collision event. Despite these revelations, many mysteries remain. Scientists don't yet know if Jupiter's core is stable or slowly dissolving, how it interacts with the metallic hydrogen above it, or how it shapes the planet's magnetic field. Exploring Jupiter's depths isn't just a scientific challenge, it's a deadly one. Jupiter's intense radiation belts, especially the one encircling its equator, pack enough punch to destroy electronics within minutes. These belts trap charged particles from Io's volcanic eruptions, creating a deadly environment for any spacecraft venturing too close. The Galileo atmospheric probe survived only 57 minutes before its instruments failed, destroyed not by heat or wind, but by crushing pressure. At the time its signal was lost, it was 150 miles below Jupiter's cloud tops, enduring pressure 23 times greater than Earth's atmospheric pressure at sea level. And that was just the upper atmosphere. To send a probe deeper into Jupiter's mysterious liquid hydrogen layers or core would require surviving pressures millions of times greater than what Galileo faced, temperatures of tens of thousands of degrees, and radiation lethal to any known material. On Earth, the deepest humans have ever sent a probe is about 7 miles down to the Mariana Trench, where pressure reaches around 1,100 atmospheres. The vessels used there are tiny, spherical, and made of titanium, far from what would be needed on Jupiter. Even if such a probe could be built, transmitting data back would be another hurdle. Radio waves can't penetrate liquid metallic hydrogen. Signals from deep inside would be blocked by thousands of miles of electrically conductive material. Any communication system would need a relay network, multiple probes passing data upward in stages until finally reaching an orbiter in space. The engineering and financial challenges are staggering. NASA and other space agencies have considered missions deeper into Jupiter, but so far, the consensus is clear: it's simply impossible with current technology. There's another critical reason NASA proceeds with caution around Jupiter: its moons. Jupiter boasts 97 known moons, most small and irregular, captured from the asteroid or Kuiper belts. But 4 are giants: Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610 and known as the Galilean moons. These aren't just satellites, they're worlds themselves. Ganymede is larger than Mercury, while Europa and Callisto are about the size of Earth's moon. All orbit within Jupiter's magnetosphere, shielded from solar wind but battered by Jupiter's own intense radiation. Io is the solar system's most volcanically active body, with continuous eruptions spewing sulfur compounds into space. This volcanic material forms a massive torus, a donut-shaped ring of ionized gas, that feeds Jupiter's magnetosphere. Europa stands out for its icy surface, covered with cracks and ridges hinting at a subsurface ocean beneath. This hidden ocean could be 100 kilometers deep, containing more water than all of Earth's oceans combined. Tidal heating, caused by Jupiter's gravity stretching Europa's interior, keeps this ocean warm, making it one of the most promising places to search for extraterrestrial life. This potential for life is part of why NASA deliberately destroyed Galileo. By 2003, the aging spacecraft was running low on fuel and suffering system failures. Eventually, it would crash into Jupiter uncontrollably. Even though the odds were slim, there was a non-zero risk Galileo could collide with Europa, potentially contaminating its ocean with Earth microbes that survived the journey through space. To avoid this, NASA chose to send Galileo into Jupiter's atmosphere, ensuring it burned up completely. The same strict precautions apply to any future missions to Jupiter. Spacecraft must be sterilized or destroyed to prevent contaminating potentially habitable moons. In 2017, Juno flew directly over Jupiter's iconic Great Red Spot, peering deep into the storm with microwave instruments capable of seeing beneath the cloud tops. What it revealed was astonishing. The Great Red Spot isn't just a surface storm. It plunges more than 200 miles deep, showing that Jupiter's atmospheric phenomena reach far below what can be seen from space. Jupiter remains a world of extremes: extreme pressure, heat, radiation, and mystery. Each new mission peels back layers of the giant planet's secrets, but also reveals just how challenging it is to truly understand what lies beneath its swirling clouds. Beneath Jupiter's swirling clouds lies a world that's as baffling as it is beautiful. The iconic Great Red Spot doesn't just hover on the surface. It plunges deep, crashing into layers where water vapor is supposed to condense. Yet, the storm keeps raging far below that boundary, defying expectations and challenging scientists' understanding of the giant planet's inner workings. For over a century, astronomers have watched this colossal storm shrink. Back in the late 1800s, the Great Red Spot stretched roughly 41,000 kilometers across, large enough to swallow Earth whole. Now, it's down to about 16,500 kilometers wide, shrinking at a rate close to 930 kilometers each year. Why this happens remains a mystery. Some scientists argue the storm is stable and could persist indefinitely, as long as Jupiter's atmosphere doesn't change. Others warn it's slowly fading and might vanish within a few decades. If it does disappear, it would be a profound loss, a cosmic landmark that's been a fixture on Jupiter for centuries, a celestial anchor point that's helped shape our view of the planet. But Jupiter is no one-trick pony. The gas giant's surface is dotted with other storms, cyclones and anticyclones scattered across its vast, turbulent atmosphere. Here's where the story gets stranger. NASA's Juno spacecraft revealed that near Jupiter's poles, these storms arrange themselves into surprisingly precise geometric formations. Up north, 9 cyclones whirl around a central storm, forming an almost perfect octagon. Down south, 5 cyclones create a pentagon. These aren't small weather systems. Each storm is bigger than the entire United States, spinning at speeds over 186 miles per hour. What's really mind-blowing is that these storms don't merge or dissipate. They stay locked in place, stable and unchanging, for years on end. Despite all our advances, no one can explain why these polar storms form such perfect shapes, or why they remain so stable. Even the most sophisticated computer models stumble when trying to simulate their behavior. The physics behind these patterns are still largely a puzzle. And keep in mind, this is only what we can observe from orbit. What happens deeper inside Jupiter, beyond the reach of our instruments, remains completely unknown. The quest to understand Jupiter is far from over. Multiple space agencies are gearing up for new missions to explore the giant planet and its intriguing moons. The European Space Agency's Jupiter Icy Moons Explorer, or JUICE, blasted off in mid-April 2023. It's currently en route to Jupiter, with an arrival planned for 2030. JUICE will focus on studying Ganymede, Callisto, and Europa, searching for signs of habitability in these icy worlds. Meanwhile, NASA launched its Europa Clipper mission in mid-October 2024. It will arrive at Jupiter a year earlier than JUICE, in 2030, and perform dozens of flybys of Europa. The goal is to analyze the moon's ice shell, probe its hidden ocean beneath, and examine its surface in unprecedented detail. Both missions will spend years orbiting the Jovian system, gathering data that will deepen humanity's understanding not just of Jupiter, but of gas giants throughout the cosmos. However, either mission will venture into Jupiter's atmosphere itself. The harsh realities of exploring the planet's depths remain a formidable barrier. Why is that? The answer lies in the extreme conditions inside Jupiter. The radiation belts are lethal to spacecraft electronics, the crushing pressures would obliterate any probe, and the immense depths make it incredibly difficult to design instruments that could survive long enough to send back meaningful data. The risks and costs of such a mission are enormous, and the scientific payoff remains uncertain. Still, that hasn't stopped engineers and scientists from imagining what might be possible in the future. New materials are being developed to endure higher levels of radiation. Innovative probe designs aim to slow descent rates, extending operational lifetimes deep within Jupiter's atmosphere. Some have even proposed nuclear-powered probes, capable of generating their own electricity in the pitch-black depths where solar panels are useless. Others envision deploying swarms of smaller probes, each diving to different depths, collectively mapping Jupiter's interior in 3 dimensions. These concepts are still on the drawing board. Nothing has been built or funded yet, but the dialogue is ongoing. As technology advances and our knowledge grows, the prospect of exploring Jupiter's hidden layers inches closer to reality. It's not fear that holds NASA back from plunging deeper, it's caution and respect. Jupiter is a savage, unforgiving environment where spacecraft quickly meet their end, crushed or fried by radiation at the atomic level. Any mission to dive into the planet's depths accepts that it will be short-lived and expensive, with limited data returned. It also means confronting the limits of current technology and venturing into utterly alien territory, where even our best predictions might fall short. There's another crucial factor: planetary protection. Jupiter's moons, Europa, Ganymede, and Callisto, are prime candidates in the search for life beyond Earth. Ensuring these worlds remain uncontaminated by Earth bacteria or other materials is a top priority. Missions must be designed with this in mind, adding layers of complexity and caution. NASA isn't intimidated by Jupiter. Instead, it recognizes the immense challenges the planet presents and acknowledges that some secrets take time to uncover. For now, scientists continue their careful watch from orbit, studying Jupiter's swirling clouds, raging storms, powerful magnetic field, and gravitational pull. They push spacecraft as close as possible, gathering data that slowly reveals the giant planet's nature. Jupiter holds a special place in the history of our solar system. It was the very first planet to form, shaping the orbits of all the others. Its massive gravity shielded Earth from countless asteroid impacts, helped carve gaps in the early solar system's protoplanetary disk, and influenced how the rocky planets developed. Without Jupiter, Earth might not even exist, or if it did, it could be a very different world. Unlocking Jupiter's mysteries means unlocking the story of our own origins. It means understanding how solar systems come together and evolve over time. It means grasping the forces that built the environment humans call home. Yet, many questions remain. Scientists still don't know exactly how Jupiter's core formed or why it appears fuzzy. The drivers behind the polar storms and the shrinking Great Red Spot remain elusive. The depth of the planet's winds, and what lies at its very center are unknown. Does Jupiter have a solid surface buried deep inside, or is it liquid all the way down? What's the behavior of metallic hydrogen within, and how does it generate Jupiter's staggering magnetic field? Every answer uncovered leads to new puzzles. Every mission exposes fresh mysteries. This is the essence of science. Jupiter isn't just a planet, it's a natural laboratory where theories about physics, chemistry, planetary formation, and the boundaries of the possible are tested on a grand scale. Exploring deeper into Jupiter isn't merely about satisfying curiosity. It's about pushing human knowledge further than ever before, about asking questions that demand answers. One day, humanity will build a probe tough enough to survive the crushing depths and intense radiation, sending back data from uncharted regions beneath Jupiter's clouds. Until then, the giant planet spins silently in the darkness, guarding its secrets and inviting the curious to keep looking upward.